Today, we want to start talking about line integrals. Line integrals are combining the two things that we just did, parameterized curves and vector fields. Line integrals are just going to be a generalization of the simple integrals that we were doing way back in Calc 1 and Calc 2, the integral from a to b of f of x dx. In that situation, we were integrating a function over an interval along the x-axis. So that was an integral over a one-dimensional thing. And that's the same thing that we're doing with the line integral. But instead of just a function that's going to give us a scalar value, our function is a vector field. And instead of just along a one-dimensional interval on the x-axis, we're integrating over a one-dimensional curve, presumably in R2 or R3, but really it could be in R anything. And the setup is the same. We have the integral over C, or the integral along C of the vector field dot dr. And all these parts correspond to the integral from a to b of f of x dx. In the integral part, we have the integral along the curve C. These are all the points that we're going to evaluate the vector field. Just like the integral from a to b, those are all the points where we evaluate the function. The thing that we're integrating is the product, the vector field dot dr. So it's a dot product, so it's a multiplication, just like f of x times dx. And in that product, we're evaluating the function and multiplying it by some small piece of the interval. And the assumption is even the same. In the simple integral, we're assuming that the function is constant for some small piece of the interval. And we're going to do the same thing here with this vector field. We're going to assume that the vector field is constant for some small straight piece of the curve. We're going to take the curve and get a low resolution version of the curve. And we're just going to have dr be some small straight piece of the curve. And that takes the place of the dx, which was some small piece of the interval. We're still trying to do a multiplication, vector field dot some points on the curve, but the vector field is variable. So we make this same assumption that we did in our simple integral. We assume that the vector field is constant at each point on the curve C, because if we take these slices of the curve to be small enough, then the vector field is mostly constant. If you look close enough, everything is flat. If your piece of time is small enough, then nothing changes. Super slow-mo. So let's make some calculations. Here are the kinds of things that we need for this line integral calculation. I don't have a clean break between this part and this part, so I'm just going to have to cut off. This red arrow is just going to have to come from nowhere. So let's start with something simple, a constant vector field and a path that's just two line segments. If this problem looks familiar to you, then you'll notice that I just stole this from the textbook. If this problem doesn't look familiar to you, then I know you're not reading the textbook. So we want to start building our intuition about how line integrals are going to work. So let's start with something simple. At each point along this curve, we're going to evaluate the vector field, and we're going to start with a nice constant vector field. So 1i plus 2j, a bunch of little vectors with a slope of 2. So we want to calculate the integral along the oriented curve C. That's what we got. We start here at 1, 1, go to 10, 1, and then go from 10, 1 to 10, 10. So it is an oriented curve. I'm going to break it into parts. I'm going to call this first part of the curve C1 and the second part of the curve C2. Want to emphasize that we sometimes will have to break up our curve, just like if we have an integral from A to B and then again from C to D, we just break it up into two integrals and then we add them together because integration is just addition. So the integral along C1 of f, the vector field, dot dr. So this is the product, f dot dr. I just need to describe the dr, the small pieces of the curve. And fortunately for us, this is why I picked a nice flat curve. So the dr part, since we're just moving along the curve horizontally, whatever the change in x is, it's going to be some change in x in the I direction and 0 in the j direction. The vector field f is just 1i plus 2j, and we're going to make the dot product with dr. And so I didn't give myself enough space. There's f, and I make the dot product with the dr, which is just dxi plus 0j. So let's calculate this dot product. I get 1 times dx plus 0. Well, plus 2 times 0. So we just get dx. So this f dot dr is just dx. In terms of dx now, I have to describe this curve C1. And since we're going from the point 1, 1 to the point 10, 1, we can describe our curve as x goes from 1 to 10. And we're just integrating the x. This raises an important question. What does this scalar value 9 mean in the context of this problem? And that's a tricky question because I did not put any context on this problem whatsoever. But the units, what this scalar would represent is what is the, just like with regular integration, it's whatever this dot product happens to represent. So when the question comes up, what are we going to use line integrals for? That's the same as asking, what are we going to use dot products for? Just like back in integration, what are we going to use integrals for? What do we use multiplication for? Area is equal to length times width. Distance is equal to rate times time. Volume is area times height. Work is force times distance. Those are all things that we use multiplication for. The calculus comes in when one of those factors is variable, continuously variable. So before we just ask, what do we use line integrals for? Realize that line integrals are essentially calculating a dot product, but one of the factors is variable. So what can we use a dot product for? That's what we can use a line integral for. That was kind of a cop out of an answer, but I'm not an engineer over here. So we got to do this part for this same calculation for C2, the second part of the curve. In this case, so this is for C1. For C2 over here, the dr is purely vertical, so it's going to be 0 in the I direction plus dy in the j direction. It's all going to be j direction. So whatever the change in y is, that's the change in dr, or that's the change in r. When we calculate f dot dr here, we'll have 0I plus, oops, that's not dr. That's dr, not f. The dot product is commutative, but why mess things up like that? F is 1I plus 2j dot the dr, which is 0I plus dy times j. So f dot dr is 1 times 0 plus 2 times dy. So now we just need to describe this part of the curve, C2, which is just the line segments from 10,1 to 10,10. So here we'll have the integral. To describe that line segment, I can just say y goes from 1 to 10, but we're integrating 2 times dy, because that's the f dot dr. So our line integral has become our nice simple integral. So this is going to be 2 times the length of the interval, so 18. Because integration is just addition, the integral along C of f dot dr is 9 plus 18, which is 20 something. Because integration is addition. So to describe dr, we want to describe small little changes in the curve. And the reason that we picked this curve is that small changes in r are just going to be whatever the change in x is. The change along this curve is all change in x. And then similarly for part 2. Here's one of the things that we want to notice. Notice that this constant vector field was 1i plus 2j. It was more up than it was right. It was pushing more up than it is to the right. So imagine, like we talked about yesterday, imagine that the curve is the path of some bird flying through the wind. On C1, the vector field is pushing, excuse me, Since that part of the path is purely horizontal, the vector field is pushing the bird along. In C2, we're just looking at the vertical part of the vector field, and that's pushing the bird up along the curve. And notice that since the vertical component of the vector field was twice as much as the horizontal component of the vector field, our line integral was twice as much in that direction. Neat. So let's suppose that we complicate things, but not too much. Let's keep this constant vector field. I like to keep things nice and simple. 1i plus 2j. So let's keep this same vector field. I don't know why I insist on drawing these by hand. I should just have some computer generate them, but then it just feels so impersonal. Besides, you'd miss out on this riveting YouTube of just like some dude drawing some vector fields. But then again, considering the prevalence of people who make a living by having other people watch them play video games, I'm thinking that the bar for video entertainment is pretty low some places. So here's what we want to do. So I want to have a path that runs from, let's say, the point 1, 8. And let's build a path that goes from 1, 8. What did I want? I wanted a slope of -3/4. So let's go from the point 1, 8 to the point -3 twice. 8 minus 3 is 5 minus 3 is 2. I hate when I have to do that because then you see how my mind works. And then I wanted a 3/4, so 1 plus 4 is 5 plus 4 is 9. So let's make a path that goes from 1, 8 to 9, 2. And let's calculate the line integral along this curve. So here's the curve C. C is the path from 1, 8 to 9, 2. So remember, our path is oriented. So from 1, 8 to 9, 2, it's indicating this direction. So right and down. There's our path C. And we want to calculate the line integral. I want to calculate the integral along the oriented curve C of the vector field F dot dr, where dr is some small segment of the vector field. So this is a step up from the last problem. I'm still using a nice constant vector field. Keep life simple. But now we're going to have to parameterize the curve, and that's going to be more complicated. How do we describe this curve C with parameters? So fortunately, even though this was just such a simple evolution from the previous problem, remember, it's the changes in the problems and the similarities that give us insight into how things work. It's not just contrast, it's compare and contrast. So you change small things and evolve your problems, and that's where we can reveal the understanding. So the great news is, even though this is just a small evolution of the last problem, by doing this small change, it will reveal all the secrets of line integrals to you, but only if I do it right now, because everybody's really invested in what's going on and everybody's paying attention. So if I do this problem right now, all of a sudden chapter 18 becomes simple because line integrals just snap into place. That bird flying in the wind, you're just going to see the calculation. It's going to be like at a movie when someone starts doing math in their head. You want to show that they're a genius, you just start throwing a bunch of math equations up on the screen, and that's them thinking about things. So do this problem, everything will become clear. But unfortunately, we're out of time for today. We're out of time for this week. That's going to do it for today. That's going to do it for this week. Think about how you're going to parameterize this curve. And then once you do, find the dot product and evaluate this line integral. That's your project for this weekend, along with the new homework that's appearing. I will see you all on Monday. Everybody have a good weekend, and thanks for playing. My dog's growling because I dropped another cliffhanger on you.